A few thousand years ago, the first human civilizations emerged, blossoming in the fertile crescent of Mesopotamia, the Indus Valley, and the banks of the Nile River. Our population, technology, and culture have been advancing ever since, until now we reach out to touch the nearby worlds around us. As our machinations turn to the stars, we wonder whether other civilizations sprung forth elsewhere before us. It seems reasonable to consider that there might be some civilizations older than ourselves out there, but could we be surrounded by older civilizations, ones even far older than ourselves? So sit back, grab a cup of tea, and join me, Professor Kipping, as today we explore the concept of civilization longevity and discuss new research from our team on this matter. It was astronomer Carl Sagan who brought the issue of civilization longevity into popular thinking with his writings and wonderful Cosmos series in 1980. Sagan reasoned that a civilization was unlikely to be in technological lockstep with us. They'll either be behind or ahead, but it would seem highly unlikely that they would be the same level of development as ourselves. Critically though, Sagan thought about communication with alien civilizations primarily in terms of radio communication. Now, since humanity has only had radio technology for about a century, then that means that if another civilization is far behind us, they wouldn't have radio technology yet and would thus be undetectable as far as Sagan's way of thinking went. But this focus on radio technology is perhaps nothing more than a product of the time. You see, in those years, the search for extraterrestrial intelligence, SETI, was framed almost exclusively as a search for radio communication or leakage. Given radio's enormous uptake as a means of communication here on Earth, this made perfect sense to those at the time. But since then, we've seen a transition away from radio to new technologies like lasers and fiber optics. Modern thinking has shifted away from a pure radio search, and these days we often speak of hunting techno-signatures. Whilst radio is certainly an example of a techno-signature, the concept is far broader and includes all manner of effects, such as detecting their orbiting satellites via transits, their cities by way of thermal emission, and even their pollutants in their atmosphere via atmospheric characterization. With this thinking in mind, it's not obvious that this basic premise that younger civilizations would be less detectable than older, mature civilizations actually holds anymore. After all, as a civilization develops, they might come up with technologies to hide, to cloak their presence. Indeed, in our team, we've even proposed a specific technique they could use to do exactly that. If you're interested in that, look down in the description for our video and paper on that topic. In contrast, a younger civilization, such as one in the midst of an industrial revolution, would contaminate their atmosphere with smog, pollutants, and synthetic refrigerants like CFCs. They could in fact be far more reckless in their effects on their planet, with long-term sustainability not yet a primary concern. But let's come back to Sagan's quote with this thinking in mind. Just stating that a civilization isn't likely to be in technological lockstep with us, that's only part of the picture. Probably what we care about more is, are they far behind us or far ahead of us? And given the fact that our emerging technologies could plausibly detect these civilizations either way, then this question takes on a new and important meaning. To illustrate this, consider the following scenario. In the near future, the newly completed 70-meter Colossus telescope detects a series of heat islands concentrated along the shoreline of a nearby Earth-like planet, which is widely interpreted as evidence for cities. We've just detected an alien civilization, but they don't know it. Now, just knowing that they have cities is rather limited information. They could be hundreds of years behind us, or hundreds of years ahead. And so as our world leaders meet to discuss their next course of action, the question as to how developed these aliens are would likely be of central importance to the decisions that are made. One can imagine military leaders strongly advising against attempting contact if they are ahead. On the other hand, if they're behind, it might be considered a low-risk venture and a chance to develop a friendly relationship early on when they're not a threat. This line of thinking got me interested in this problem, especially in light of how the modern technosignature era was overturning many of the assumptions and conventional logic of Sagan's era. Even if we ignore the question of contact or detection, the issue as to whether nearby civilizations around us are going to be more developed or less developed than us is clearly one of enormous import. And I have to admit, it's a lot of intellectual fun to ponder such questions, to try to figure out our place in the cosmic scheme of things. And so I got together with Dr. Adam Frank and Dr. Caleb Scharf to take a crack at this in a new paper that I'm happy to say has recently been accepted for publication in the International Journal of Astrobiology and is linked down below. A modern take on Sagan's musings, if you will. In order to make progress on the question of civilization longevity, we need a mathematical expression that describes the statistical distribution of lifetimes. Recall that a statistical distribution just describes how the various possibilities are spread out. For example, a uniform distribution describes the roll of a dice, since all possibilities are equally likely. Now, we're going to spend a bit of time on this because it's really critical to the final result. On the face of it, determining the distribution for the lifetimes of technological civilizations seems like an impossible task. How could one possibly make progress on that? I think it's that aspect that actually drew me towards this problem, as probably regular viewers of this channel might even recognize. Look, even though one could write down almost any formula imaginable for this problem, each one wildly different to the other, in nature, we find that there's just a handful of distributions that seem to crop up all the time, as if nature herself has a preference for them. Perhaps the most famous case is the Gaussian distribution, also known as a bell curve. A good example of this might be to chart the heights of, say, American men. Now, since the environment and genetics display fairly minor variability, there is a convergence of heights at around 5 foot 9 inches, with some fluctuations around that mean, tailing off towards the edges. Now, since we want the lifetime of civilizations here, the life expectancy of individual humans might seem like a useful point of comparison. And looking at that distribution, we can see that it is a bit different in shape, but could be argued to be approximately Gaussian too. So, on that basis, could we use the Gaussian distribution for alien civilization lifetimes? There are good reasons to think not. Gaussians do a reasonable job of explaining the distribution of human life expectancy because factors affecting our survival, such as medicine, shelter, nutrition, are widely available, although frankly not as widely available as they should be. But imagine without that reliable food source, every week would become a gamble. Will you find food or won't you? If that probability of not finding food is even 1%, then after 100 weeks, there is a reasonable chance that you will perish. In other words, we live each day under constant risk, and the longer we persist, the more likely it is that we will eventually fail. Whenever you have a constant risk to your survival like this, exponential distributions naturally arise, not Gaussians. For example, if we measure the lifetimes of gazelles in the wild, as shown here, The constant daily struggle for survival they face means that longer-lived gazelles are rare, but fawns are very common, a nearly perfect exponential. In fact, exponentials crop up all the time in cases related to survivability, whether it be the failure rates of aircraft components or the lifetime of your smartphone battery. Individual human lifetimes don't look exponential because the accumulating risk of death each week is so small that our lives are often truncated by health problems that develop later in life rather than, say, malnutrition. But disparate technological civilizations is clearly a very different problem. Their survival each year, each century will face existential threats. That means that their distribution lifetimes will more closely resemble that of aircraft failure than that of, say, a 21st century human. For example, let's take the rate of meteorite impacts. A large meteorite, such as the one hypothesized to have extinguished most of the dinosaurs 65 million years ago, clearly presents an existential threat. If we look at the time between such impacts, using cratering data from Earth and the Moon, we indeed find another exponential distribution. In fact, one can even prove mathematically that for events which arrive randomly, but with a fixed average rate, that's known as a Poisson distribution, the time difference between each event must follow an exponential distribution. This is a general feature of the universe, not just limited to meteorite impacts or aircraft failure rates. Now yes, we might soon develop the ability to protect ourselves from meteorite impacts, but that is just one threat amongst an almost endless list. Gamma ray bursts, nearby supernovae, a destabilizing stellar flyby, magnetic field shutoff, an extreme volcanic event, planetary instabilities, obliquity drift, nuclear war, climate disasters, global pandemics. Look, you get the idea. You've lived through 2020. The real point is that if these existential threats carry a small chance each year of occurring, then the lifetime of technological civilization should follow an exponential distribution. There's something amazing and almost terrifying about this whole process. Here we are, thinking apes, just sat on a ball of rocks spinning through space, using our minds to ponder existential questions. And yet, just using our minds and some logic and some reason, we are able to deduce that the lifetime distribution of technological civilizations is most likely exponential in nature. Now, we should of course remain skeptical about the validity of this. After all, any hypothesis requires data to verify. But here we have a solid argument to propose this as the leading hypothesis to explain this distribution. Crucially, hypotheses need testing against data to become accepted models. Now here, we don't have data for alien lifetimes, at least not yet, but we can do the next best thing and look at the lifetimes of species here on Earth. Using the fossil record and radiometric dating, we can see how long different species persisted in Earth's own past. Plotting up the data, which I'll link to down below in the description, one can see that indeed the data are well described by an exponential, where here the mean or average lifetime is 70 million years. Now the skeptics amongst you might say, look, this is all well and good for the lifetimes of generic animal species here on the Earth, but that's not applicable to intelligent beings such as ourselves. This doesn't prove that civilizations, ultimately a rather different phenomena to mere species, must necessarily follow an exponential distribution when it comes to their lifetimes. So, to address this, there's one other thing we can compare to: the lifetimes of past civilizations here on Earth. Human history is punctuated by the rise and fall of civilizations, and we can date how long they last from archaeological evidence. After all, even the grandest of civilizations eventually meet their demise.
I wonder if the Emperor Honorius, watching the Visigoths coming over the Seventh Hill, truly realized that the Roman Empire was about to fall. This is just another page in history, isn't it? Will this be the end of our civilization? Turn the page.
This figure, with the source linked down below in the description, beautifully shows the timeline and lifetimes of past civilizations. If we plot this as a histogram, the data are a little sparse, but the overall pattern is indeed like an exponential, characterized by a monotonic decline from zero. One thing to keep in mind here is that this dataset is surely incomplete, especially at the short end. Let me explain that statement with an example. If a civilization lasts for a century or less, then it will leave less evidence behind for us to discover, and so we're more likely to miss them. You can see this by fitting an exponential distribution to just the data greater than 200 years, shown here by the white line, and then we draw it back to zero. And as we see, this predicts that we're probably missing around 30 short-lived civilizations in our dataset. Overall though, this suggests a mean lifetime of a few hundred years typically. So I think at this point, it's fair to say that we have multiple lines of reasoning and evidence to indicate that an exponential distribution is the most plausible hypothesis for the shape of technological civilization lifetimes. But critically, an exponential distribution is actually useless unless you know the rate of change of that exponential distribution, the slope of it, and that's characterized by just one parameter, the mean lifetime. If the mean lifetime of the population tends to infinity, then the exponential becomes a uniform flat line with all possibilities being equally likely. But with an ultra-short mean lifetime, it becomes a cliff face. Recall that from earlier, using Earth animals, we found 70 million years for this number. But from human civilizations, we get a few hundred years. But what about technological civilizations? Really, neither of these previous categories are quite what we need, so even though the shape is likely exponential, we don't know how steep that exponential truly is. At this point, you might be thinking, we're stuck, that's it, there's no way forward from here. Hey, we've come all this way, but now it's time to give up on this endeavor. How can we possibly learn the slope of the exponential for the lifetime of technological civilizations if we don't have a sample of technological civilizations to look at? Well, actually that's not quite true. We do know of one technological civilization, it's us, ourselves. And although we don't know the ultimate end of the story, we do have a minimum constraint on the lifetime of our civilization. Now, you often hear it said that a single data point teaches you nothing. And I want to be very clear with you. That is wrong. To see this, imagine I go from one data point to two data points. What happens then? Well, according to this fallacious rule that one data point teaches you nothing, we would suddenly go and quite remarkably transition from knowing nothing to knowing something as we go from 1 to 2 data points. But there's nothing inherently special about the number 2. The truly significant change happens when we go from 0 data points, which by definition means we have no information, to 1 data point, which by definition means we have some information. Now, if that sounds confusing, think of it like this. 1 data point is like 1 drop in the ocean, but what is an ocean but a multitude of drops? A rich dataset is indeed a collection of single data points, and each point provides information.
For what? No matter what you do, it will never amount to anything more than a single drop in a limitless ocean.
What is an ocean but a multitude of drops?
So let's go ahead and try to learn the shape, the slope of this exponential distribution from just 1 data point ourselves. Now, if you've seen our previous videos on the topics of the odds of life and intelligence in the universe, or even more recently, the possibility that we might live in a simulation, then you can probably guess how we're going to tackle this problem. That's right, you guessed it, we're going to use Bayesian statistics. For the uninitiated, Bayesian statistics is really just a school of mathematics devoted to problems just like this, ones where you have limited information in hand but are trying to uncover the truth behind the data. When one uses our singular data point with the exponential model in a Bayesian framework, we find that the most likely mean lifetime of a civilization is twice that of our current age. There is of course a broad range of values around this which are nearly as good, but a clear peak emerges as you can see here. In a way, this is very intuitive. Although we did not impose the principle of mediocrity here, we naturally recover something resembling it, since we find ourselves at the halfway mark of this mean lifetime value. You'll notice that I'm being deliberately evasive about giving you specific numbers here. I mean, what is our age as a civilization in years as of right now? Well, the reason I'm not going to give you that number is because it doesn't matter. It doesn't affect what I just told you. You can define age in many different ways, but however you do, the statement I just told you is still true. For example, if we define a technological civilization as beginning with the invention of radio, then our age would be about a century, and so the mean lifetime of radio-centric civilizations is twice that, 2 centuries. But someone else might instead define it as beginning with the industrialization period, or the development of cities, or even farming. Indeed, all of those changes mark key transitions, and ones that could be plausibly detectable in the foreseeable future as a techno-signature. We can argue about definitions, but the basic result that the most likely mean lifetime is twice that of our current age is a general result of this analysis that holds irrespective of that discussion. Now, mean lifetime is one thing, but it's really just part of the story, because that mean, or really an average, just characterizes the slope of the exponential distribution. Recall that the exponential has a very long tail, and so, in some rare cases, there will be civilizations that last many times longer than our current age. If a civilization has a lifetime that's, let's say, 10 times that of our current age, then the typical age at which we would find that civilization would be about halfway, so 5 times of our current age. So to give this some context, what this means is that civilizations that have a lifetime greater than twice of our current age will have a current age likely exceeding that of our own. In other words, they are older civilizations. Let's add up how many civilizations that is, which we can do through a little bit of calculus, and that gives us about 40%. And so, in turn, that means that the other 60% are likely younger in age. So at this point, we could stop and claim that this was our result. Look up into the sky at the nearest civilizations, and one should find that amongst them, there is a more or less even split between younger civilizations and older civilizations, with a slight preference towards the younger ones. But actually, this is wrong, because we have ignored a crucial subtlety that is going to change everything. A simple yet critical effect. Time. I think the best way to explore temporal bias is to see it. Let's create a little simulation. Imagine that I'm looking at some volume of space from above, represented by this square. Now let's whiz through time and watch civilizations pop up randomly in this region. Each civilization has a different but random lifetime, which I'm going to determine by drawing from our exponential distribution. If the civilization has a lifetime greater than twice our current age, I'm going to color it red. These are civilizations that will likely outlive our own. On the other hand, let's color the shorter-lived ones in green. Remember that with our best guess for the exponential distribution shape, roughly half of them are shorter lived than us and the other half are longer lived. In fact, let's just tweak the exponential a little bit to make that an exact rule, a perfect 50-50 split, just to keep things simple and clean in our visualization here. So as time flitters by, we see civilizations pop up, each one with a random lifetime drawn from the exponential. Let's keep track of the fractional number of green versus red civilizations that we've created with this bar chart on the left-hand side. After an initial settling in period as the simulation begins, it rapidly converges to the 1/2 value that we expect. Great, but as we watch the simulation play out, despite the fact that we are birthing even numbers of red and green civilizations, one can't help but notice that there seem to be more red dots than green. What's going on? To see if this is an optical illusion, let's put another bar chart over on the right hand side, which shows the fraction of green versus red civilizations in each instant. Not ever, but just in each snapshot in time. As we suspected, there is indeed a consistent shift towards the red civilizations. Even though red and greens are just as likely to be born, we somehow end up with more reds in any given moment. Some of you may have figured out what's going on here. The longer-lived civilizations appear more common simply because they hang around for so much longer. Look, the green ones are born just as often, but their short lives mean that they quickly disappear off the map. As a result of this, when we look around us in space, we should expect that most of the civilizations around us will be longer-lived ones than ourselves. Temporal bias. We can even take this a step further and consider the age of these civilizations rather than their lifetime. Lifetime and age are of course related, but different concepts. You can think of lifetime as just being the age at which the civilization ends. Let's use the exact same simulation as before, but now I'm going to color the civilizations by their age, from young in green to old in red. In fact, if you look closely, you'll see the dots morph in color as they age right in front of your eyes. Let's throw up another bar chart on the right hand side to see what's going on. Here, I'm counting up the fraction of civilizations which are younger than us in green versus older than us in red. Now, the age bias is not quite as extreme as the lifetime bias, but again, we see a shift towards the red. What this means, in simple terms, is that if alien civilizations are out there, and their lifetimes are distributed following an exponential distribution, as we have good reasons to suspect, then the natural consequence would be that most of the civilizations around us would be older than us, not younger. This is a profound and very important result. It would mean that we are surrounded by ancient aliens. And no, I'm not talking about aliens visiting and building the pyramids or some other nonsense. I'm talking about the statistical properties of their distribution as affected by this temporal bias effect. We actually even can give you a ratio of how many civilizations are younger versus older than us. Using the Bayesian framework from before, we find that about 25%, a quarter, of civilizations should be expected to be younger than us, and 75% older. So what that means is that amongst the 4 nearest civilizations to us, 3 are likely older. So if we come back to my thought experiment of detecting an alien city at the beginning of this video then, the conclusion of our paper is that the chances are, in the absence of any other information, that they would indeed be older than us and thus plausibly more advanced. Now the next question you might wonder is how much older than us could they really be? Well, the nature of the exponential distribution means that that tail drops off pretty quickly, and so civilizations which are much, much older than us are likely to be very rare, even accounting for the temporal bias effect. Breaking it down, we find that approximately 10% of civilizations would have an age greater than 10 times that of our own. Now, that might sound like a low chance, but amongst the 10 nearest civilizations, that means that one of them is more than 10 times older than us. Given the rapid pace of technological development over the last century here on the Earth, the mind boggles as to how much more advanced such a civilization could be. How would they think of us? Those results represent the key insights of our paper, but I want to emphasize that we don't know how often intelligent life evolves on other planets. It could be that there are no civilizations in our stellar neighborhood or even in our galaxy, and thus when we speak about the nearest civilization to us, that could be someone who's on the other side of the universe, or in contrast it could be someone who's just a few dozen light years away. Either way, it doesn't matter. The results of our paper are the same. Those nearest, closest civilizations to us would likely be older. For me, this paper is important because it changes the way we think about looking for intelligence. Our notions of contact and communication radically change when we consider that they would likely far exceed us in technology. After all, how would we react if a hunter-gatherer society in the Amazon rainforest sent us a message floated down the river on a piece of wood? Would we begin jumping up and down at the chance to initiate communication? Or would we simply leave them be? I don't know the answer to this. Let me know what you think though down below in the comments. How would interactions between these unbalanced societies occur? Fermi's paradox can be explained through a myriad of possibilities. For example, it is possible that we are just alone in the universe, the only technological species, a possibility we have discussed here on this channel before. On the other hand, perhaps there are other technological species out there. It's just that the gap in technology between us and them is so vast that there no longer exists a two-way benefit to communication. Either way, I hope I've shown you that as hopeless as the problem might seem at first glance, we can actually, and quite remarkably, make some reasonable deductions about our possible neighbours using just the tools of statistics and logic. For now, perhaps that's the best that we can do. Here in the Coolwoods Lab, we're going to continue to push the envelope about the limits of what we know, to tackle these fundamental questions about our place in the universe. We refuse to stop being curious, and we hope that you'll join us for the ride. Indeed, the research that I've spoken to you about today was partially supported by donors to our group. Donations that support real research in our team, and that you too can now join by clicking the link down below in the description. So, until the next video, stay thoughtful and stay curious. Thank you so much for watching, everybody. I'm sure this video will spark lots of fun discussion, so please do put them down below in the comments. I also want to take the opportunity to thank two of our new donors. That's Martin Krobel and Jeff Suter. Thank you so much for your support, guys. Your donations are helping us to make real research advances here in our team. So until next time, have a great day and see you around the cosmos.